All right, let's get started for real this time. So last time I didn't quite get as far as I wanted to with context-free grammars and the grammar you'd need for project one. Some students have already started trying to tackle project one, which is great, and inventing their own ways to do it, which might be a little bit of a slog. So hopefully what we go over today will give you one suggested way to write a parser for this class. So we're going to use a recursive descent parser. But first, we need to work with our grammar a little bit, because the grammar I've given you is actually won't work directly with recursive descent. There's a little bit you have to do in order to get it to work properly. But before I begin, any questions from last time or questions about project one? Nothing? So just a reminder that it's looks very much the same like project zero, except now the operands of our expressions can take nested expressions. So we have this kind of recursive structure of our language. And context-free grammars is how we can express this kind of language. And if you remember from last time, regular expressions cannot express these kinds of languages. These kinds of languages are not regular languages. I also had made a mistake last time where the right operand was just a number and not an expression. I've corrected this grammar everywhere on the site. So now, in case you had looked ahead at this, now expressions, each operation can take a nested expression as both of its operands. But anyway, hopefully nobody went that far ahead and didn't catch that. We're not tripped up by that mistake. Okay, so just to quickly review last time. This is what the grammar for our new expressions looks like. As I just said, it allows for nested expressions. And so what we get is this, we get this recursive definition for the operands, but we still have an expression. Expression can just be a single number as well. And so if we think of this as recursion, the productions that have a nested expression in them are kind of like the recursive step, whereas the productions that just have a terminal or don't have the self-referential expression, the self-reference to the non-terminal, it's kind of like the base case. And that's exactly how our recursive descent parser is going to look. We're basically going to do a straightforward transformation from this grammar to a recursive program. But before I get there, let me go over real quick, just go over context-free grammars again. So who can tell me, there's 4 parts to any context-free grammar. Who can tell me what one or more of these are? Does anybody remember what you have to do to specify a context-free grammar, or what the pieces are in any context-free grammar? Anybody remember? Non-terminals, yeah, so non-terminals. So expression is a non-terminal. What else is there? Terminals, so plus and minus, number, these are terminals. What else is there in a context-free grammar definition of a language? Yeah. Productions, yeah, good. So productions take non-terminals and they show how you can substitute a non-terminal with another sequence of symbols. So an expression can be substituted with expression plus expression. What else? There was one more piece, yeah. The starting symbol, yeah, good, the starting symbol. So just like in finite state automata, you had a starting state and a final state. So same idea, you got to start somewhere when processing this language. So just very quickly, let me go over derivations again. So if I've got this string in my language, 2 plus 3 times 7, for instance. If I want to derive this string at the bottom from my starting, assume this expression is my starting non-terminal, how do I derive that string using this grammar? So just as a quick refresher from last time, this notion of these context-free grammars comes from linguistics, comes from Chomsky's view about linguistics, that these grammars are rules about how you generate strings in the language. And they work by starting at the starting symbol, and then your brain, or whatever machine in your brain, this is the theory, picks these productions in order to start generating an utterance in the language. So a derivation is a sequence of these steps going from the starting symbol, applying productions to produce a string in the language. Yeah.
So we gotta see what the first starting.
Yeah, what the first step.
Plus expression.
Yeah, so well, expression plus expression. I'll just write XPR. And so that would be one valid first step in this derivation from expression to this string in the language. And so we can actually start. Yeah. So that's the first step in doing a derivation in this language. So what would come next? Say we're going from left to right, doing the left to right derivation. Yeah.
Would we replace expression with num at this point?
Yeah. So we can replace expression with a number. And that's really the only thing that can be replaced at this point, because if there's a plus to the right of num, then there's no other choice that's valid at this point. There's no parentheses, there's no other operators that would come before the plus. So what about the second expression? What would that get replaced with?
Expression times expression?
Yeah, good. So just expression times expression. And that corresponds to 3 times 7. And then if we continue doing this, there's really only one option for each of these expressions. They will both have to be at this point the number token at this point. So questions on this? Any questions on this? This was, yeah.
Would it be okay to, instead of starting with expression plus expression, to start with expression times expression?
That's actually a really good question. So you definitely could have started with expression times expression and still done a derivation. So let me actually show that now, so that's a good question. That's actually what we're going to go over today. So let's take this same string in our language, 2 plus 3 times 7. And I'm going to write it here twice for reasons that you will see in a second. So as I mentioned last time, these derivations can be represented as a tree, as where each node of the tree is a non-terminal from the left-hand side, and its children are the production that you applied. So taking the derivation, the leftmost derivation that we just did for 2 plus 3 times 7, we can represent this as a tree structure. So the first derivation was expression plus expression. So those are the child nodes, and I'm just going to draw an arrow directly to the token of the language. And the left-hand expression was just replaced with a number. The right-hand expression was replaced with num. Sorry, not replaced with num. It was replaced with expression, the multiplication symbol, and expression on the right-hand side. And then each of these expressions was replaced with a num. So questions on this? Any clarifying questions? Is everybody with me on these derivations and parse trees, how they relate to the grammar and the input? Questions about this? Everyone's good? What? So far. Okay. So as your classmate asked, what if we, instead of starting with expression plus expression as our first production to apply, what if we started with expression, the multiplication symbol, followed by expression? Can we also derive this string, 2 plus 3 times 7, can we derive this string from the same grammar? So let's see, can we do this? What do we replace the left-hand expression with in this case? Expression plus expression. And then what productions do we apply? Everything gets turned into a number, yeah. All of these expressions get turned into a number. And just as a little reminder, if you look at our grammar, so we applied this first production, we applied the times production, and we applied the expression goes to number production. Those are the substitutions that we used for this derivation. But notice that there are two different trees, two different ways to derive this string from the same grammar. And so the question for us is, as compiler writers, if we have two ways to interpret the syntax of a statement, what does that mean for us? So to give some intuition behind this, so we already covered this. To give some intuition behind this, this is called ambiguity in language. And we see this even in human language. Actually, there's a lot of ambiguous statements. But this is syntactically ambiguous. Ambiguity means a lot of things, but the kind of technical meaning is that there are multiple derivations of the same string. So one example of this in English is the passerby helped dog bite victim. So this is a funny one because it has very different meanings to us. But the reason is actually because they have two different syntactic structures. So who are you helping? You're either helping the dog or you're helping the victim. There's two different ways to do sentence diagramming on this same sentence, and they lead to two very different interpretations for us. But the relevant part for us is that if we had a grammar for English and we were to do a derivation, subject, verb, object, and then break it down into noun phrase and extra clauses, we'd end up with two different parse trees for this sentence, and that's kind of gives us this connection between syntax and semantics. That there's some connection here. That the meaning of a sentence kind of depends on what its syntactic structure is, which is kind of, I think, underlies why you have this Chomsky innate linguistics. But for us, for writing a programming language, now the grammar does not ascribe any meaning to these symbols. We know plus. We want plus to be addition. We want times to be multiplication, or the star symbol to be multiplication. But we're the ones giving meaning to that. We're the ones writing a program that gives meaning to that. But if we want to turn this into arithmetic, what do these two different syntactic structures mean for this expression, for this arithmetic expression? What is the difference between them for how we want to interpret them as arithmetic? Yeah. Well, there's two different solutions. Yeah, there's two different solutions to this. There's two different ways to compute it. Well, why are there two different solutions? The order of operations, yeah, the order of operations. So if we interpret this, tree, this expression tree, and I think a lot of you have done like infix to postfix computation and maybe expression tree evaluation. Have you done expression tree evaluation where you have a tree of the no? Well, yeah. So the infix to postfix problem is very, very similar. You're effectively doing parsing of the input without realizing, and you're writing kind of a special purpose parser for infix to postfix. But what's going on when you want to evaluate, for instance, when you want to evaluate postfix, if you were to turn that postfix expression into a tree, which basically it is just a tree, then you would do a post-order traversal in order to compute the value of this expression. So you start at the top and you say, well, how do I compute this plus? Well, I have to get the value of the left-hand side. The value of the left-hand side is just 2. And I have to get the value of my right operand. So what's the value of my right operand? How do I get the value of my right operand? Yeah, I just recursively evaluate the right-hand side. And how do I evaluate how do I evaluate an expression? Well, I just look at its two operands, the left and right operand, and whatever values those happen to be, I do the multiplication. And so now I know the right-hand side of my top level expression is 21. I'm bad at math. Is 21. So now I can finally complete my addition operation. So in terms of order of operations, which operation happened first? Here. Multiplication, right? Multiplication happened first. Even though it's lower on the tree, because we're doing a post-order traversal, that actually means that operation happens first. We don't compute the expression until we know the values of both children. What about this right side tree? What happens with the tree on the right? Well, we could go to compute the left-hand child, and we find that we have another nested expression. I'm sorry, in the left-hand child, we have another expression. So what do? We have to recursively compute this addition expression. So we get 2 plus 3, which is 5. And then before we can compute the multiplication, the top level multiplication, we have to find the right-hand side, which happens to be a leaf node, which happens to be 7. So we get 7 plus 5. Is that right? 5 plus 7. And we get 12. So we get 2 different answers, which is exactly what your classmate said. So walking through this and seeing that we get the operations happening in different orders, what is the, for us, what is the difference in meaning between these two ways of parsing our sentence and our parsing our expression with our grammar? What's the difference between them? What's that? Well, the solutions are different, but like, why are they different? The order of operations is different. But okay, so for us, which one would you want to have in your programming language? Which do you think is, the right one, or the one you prefer? The left one. Why? Why? Because like PEMDAS, right? Because the PEMDAS order of operations, that's what you're all taught. But there really is no right answer. This is up to you as the person implementing the language. You have to define what you mean by these parses. One is not right and one is not wrong. In fact, there are programming languages where the tree on the right is how the programming language processes. Like Fortran, for instance, does not respect these PEMDAS order of operations. It just does left to right, unless you put parentheses. So neither is right or wrong. We look at these symbols and we ascribe meaning to them, but we're writing a machine that is going to implement the meaning of this language. And so at this stage of parsing, there is no meaning of the language until you write a program that interprets what these operations mean. Okay, so for our language, we are indeed respecting this PEMDAS order of operations. So we want to have the right-hand side, always. The problem is there are two possible derivations for this string in the language. So what do we do then? How can we solve this in our compiler? So assuming we can actually do this parsing problem given a string in the language, assuming that we can construct a parse tree for it, let's say we can do that. How do we make sure that only one of these parse trees is going to be used? Any ideas how we might be able to do that? Yeah.
Can you use something like postfix or something?
Well, the program is given to you in infix. So then how would postfix help you here?
I mean, you can translate it to that.
You could translate it to postfix. Okay. But in postfix also has to you have to make a decision about order of operations in postfix as well, right? So I guess there's like an algorithm. Yeah, there's an algorithm with postfix where you can, you push the lower order operations onto the stack and you wait until you see a higher order one. So yeah, that's one way you could do it. You could just translate this using that postfix algorithm that you know about. That's one way. Yeah, you could do that. Yeah.
You could add another term.
You could add another term. What do you mean?
Like, or you could add another expression, not expression, but another.
Yeah, that's right. So you could actually modify the grammar itself. So instead of allowing an expression to have any operation, you could restrict expressions to only have certain operations. So this is exactly the solution I'm going to go over today. So thank you for that. Thank you for bringing that up. You could say that at the top level, whenever you see an expression, disallow multiplication and division, so that only addition is allowed within expressions, and then just create other non-terminals for multiplication and division. So to see what this looks like, so I already kind of went through this. So to see what this looks like, let's take our original grammar, and I'm going to start writing this with a single character instead to make it a little faster. So our original grammar looked something like this. So I'm going to use the kind of dragon book notation just because it's a little faster. And I'm just going to say num. So now num is I want you to kind of be aware of these two different notations. So when you read the dragon book, just be aware that num is the tokens are going to be like bolded words, whereas the non-terminals are going to be uppercase characters. So if this is my original grammar, I want to add a different non-terminal that's just for multiplication and division. So what that means is my new expression will disallow, it'll disallow, this one right here is going to be, the multiplication is going to be removed from my expression. Actually, let me motivate this a little bit better. So I'm going to have some other expression that I'm going to call, or some other non-terminal that I'm going to call t, and T is going to have multiplication, whereas E is going to do addition. But how are they related to each other? So I can, if I do, well, let me just tell you the answer since I have a lot to get to today. So the way we're going to do this is we're going to create new non-terminals for expressions, terms, and factors. So if you remember the terminology we use for factors, those are things that can be multiplied or divided. Terms are things that can be added or subtracted. So we're just going to make those explicit in the syntax of our language. So an expression then becomes either an expression plus a term or just a term if there's no addition in the sentence. And a term becomes a term times a factor or just a factor if there was no multiplication in the sentence. And then the factor will hold our leaf nodes. So the factor can just be a number. But remember that we also have in here, which I didn't show, we also have parenthesized expressions. So how do we fit these parenthesized expressions into our new grammar? So we've got a new non-terminal for terms that are syntactic units that are added together, a new one that for syntactic units that are multiplied together, and then factor for just the terminal. But what about parenthesized expressions? Where do they fit in this order of operations? Where do they fit in this grammar? Any thoughts? Yeah.
You could make a counter for them to count how many you need to get to match the other.
We could count them, but how can we do this in our grammar? So sure, we could write an algorithm specifically for parentheses, but we already went to the trouble of making a new grammar based on your suggestion, actually. So how can we encode that nesting depth in our grammar? So keeping in mind, so before we had the parentheses at the expression level. Oh, okay, so what is the order of operations for, like the PEMDAS order of operations for parentheses? They're at the top level. They're at the very top level. So they bind more tightly than anything. And so the E has the least order, has the lowest order. T has is higher than addition. So we can put the parentheses as a factor. So whatever is inside of parentheses is basically just like a number. It's basically just like as if it were just a single number. Well, anyway. So questions on this? Questions on this? Yeah.
Since there can be nested parentheses, should there also be one of like parentheses and then another parenthesis and then the expression?
That's an interesting question. So since you can have nested parentheses, how do we deal with expressions that have multiple nested parentheses, or what's going to happen? So let's take a look at this grammar and see. Let's see if I can make some room on the right here. So let's take a string in our language. Let's say we have, well, to avoid getting the tree too deep, let's say we just have this expression in our language. So according to the definition I gave you, or in C, for instance, this is legal, right? This is legal in C. You can do this in C. You can add unnecessary parentheses. So assuming we're starting from the E non-terminal, how can we derive this string from our grammar? So what is the first production that gets applied? Say again?
LP, RP.
Say again?
LP.
LP. So which production of E has a parenthesis in it? So remember, we're trying to replace E with one of E's productions. Say again? Well, there's only two productions for E. There's E plus T, and there's just T. So which of these productions can replace E? Say again? T. Yeah, so there's no plus symbol in our string, so there's no way it could be E plus T. The only other option is T. I mean, maybe there's no way to parse maybe there's no derivation of this string. Okay, so now we have the T non-terminal. What production do we replace T with? F. F is the only choice we have. What about, now for F, what do we replace it with? Is it parenthesis or is it number? Parenthesis, right? So the first, reading from left to right, the first symbol is a parenthesis. If we just chose number at this point, we wouldn't account for all the characters in the string. So it must be parenthesis, E, parenthesis. Now, why isn't it, say, this parenthesis? Well, we haven't encountered the right one either. We know we're going to encounter one because of the production. But how do we know, like, what would happen if I picked the near parenthesis to 2?
Then you would have leftover parenthesis.
Yeah, you would have you would not be able to match the second parenthesis. Say again?
We wouldn't be using a stack implementation, right? If we match the first left with the first right.
Yeah. Well, let's get to implementation. We'll get to implementation. We'll get to implementation in a bit. It doesn't necessarily have to be an explicit stack to implement it. So I'm just going to move this down a little bit because I need more room. Okay, so when we replace E with something, we have to match, ultimately we're going to have to match all of the characters from the production. So this production says a left paren E and a right paren. So I know ahead of time that this rightmost paren is going to be what's matched. But you could, when you're parsing, you actually don't know that ahead of time, and we'll see how that's handled. But okay, so what is this next E replaced by? T, and then F, and then number?
Oh, no, parentheses, no.
Parenthesis, E, and then we have to move this yet again because this is a very long parse tree. Move this yet again. So we get F, and F expands to parenthesis, E, parenthesis. And then we just go on again. Now we're back at E again. So we replace it with T, F, and finally F can be replaced with a number. Questions on this? What are your questions on this? How will this get put into code? Okay, that's what we're going to see. That's what we're going to see next. Any questions on this? Does this make a little more sense doing these derivations? Okay. Yeah. So I think you have this for homework as well, doing these. Yeah. Yeah. This is the new grammar for project 1. Yeah. So subtraction and division are at the same level of. They have the same order. The same. Yeah. So they're going to be here. So actually, your homework is going to be to rewrite the grammar. That was your homework from Tuesday, which hopefully they did. Did you talk about it in lab at all? Yeah. So I think in lab they talked about the same thing, talking about changing this grammar to respect order of operations. Yeah.
And mod is with division, right?
Mod is the same height or same precedence as division. That's right. So then, good question. How do we actually implement a program that can do this? Now, one of your classmates last time mentioned recursion. So recursion, there are actually many ways to deal with this. Formally, these context-free grammars are equivalent to a push-down automaton, which if you're taking big discrete, maybe you're learning about. That's just a finite state machine plus a stack. So all the intuition about using a stack or recursion, stacks and recursion are kind of closely related, but that's the crux of what we're going to have to do. At some level, we're going to have to process a production and then store some state onto a stack and wait until we finish processing nested structures. So the The algorithm I'm going to recommend that you use, and there are lots and lots of different parsing algorithms. We'll go over another one in a week or two. But I think one of the simpler ones to implement, especially if you understand recursion, and it's actually a really good way to get better at doing recursion, is called recursive descent parsing. And so, the parsing problem that we talked about last time, the parsing problem is, instead of going from starting symbol to language, the parsing problem is, given some string in that language, figure out what the derivation of that string was, if there is one. That's the parsing problem. And that's what our compiler has to solve, because we're not given the grammar and we're not just trying to generate, random programs. We're trying to take a specific program and analyze its syntactic structure. That's the parsing problem that we have to do. So there's a lot of ways to do this. They're kind of grouped into two main categories. One is top-down parsing, and that's kind of like the use of grammars as generative grammars that I just walked through for the derivation. But we start at the starting symbol and try to guess which production should be applied at the next step. But if you work through a very, very long string, it may be very hard to figure out what production is going to come next. So for a more general case, you can use backtracking. Has anybody heard of backtracking? You guys go over this yet? So you can do recursive descent with backtracking and just basically try every production, and then continue this recursive expansion. If you're wrong, you just pop back up the stack and try another production again. But we're going to use a faster algorithm called predictive parsing, where we're going to be able to guess exactly, for certain grammars, we're going to be able to guess exactly which production to use. So that's top down. Start at the root node and try to construct the tree, or try to derive it from the starting symbol to the string. With bottom up, you look at the input symbols and try to match you start from the leaves of the tree and build the tree from the leaves to the root node. And I'll go over an algorithm for that in like a week. It's in the syllabus, so I'll go over an algorithm for that later. But for your implementation, I recommend doing this top-down predictive parsing approach. But of course, if you're adventurous, pick any other parsing approach or invent your own. Okay, so the core of any recursive descent parser is to treat every non-terminal as a function in your parser, and then the production defines the body of that parsing function. So for instance, this program non-terminal, the program non-terminal consists of 0 or more statements. So the way we translate that into code is we have one parsing function called program, and just like with implementing a lexer or regular expressions, we just turn that into a while loop that repeatedly reads in a statement. Now, this is kind of pseudocode. You have to check for the end of file, white space, and do all your lexing and everything. But in terms of like hand-wavy pseudocode, we're going to loop until we're done reading a statement each time we iterate, reading a potentially arbitrary number of statements. For our statement, so for instance, when we have print expression semicolon, like in project 1, this is basically going to look just like project 0. You check for the print token, you call the expression kind of subparser, and then you check for a semicolon token. With me so far? Any questions on this so far? So it's almost straight, like almost one-to-one correspondence between statements being functions and the production, or non-terminals being functions and their bodies being the body of those functions, the productions being the bodies of those functions. Now, what about factor? So factor is a little bit different because we have alternation. But similarly to lexing, how do we handle cases where we have two different possible productions that we could track? So we could just do this recursive descent approach and just search the entire grammar for every possible parse of this string. But what can we do that's closer to lexing that would be faster? What can we do in this case to distinguish between these two productions? Yeah. Say again? Yeah, you can use a look ahead. So you can look ahead one character or one token, depending on how you implemented your lexer. And you can actually, in this case, you can determine exactly, you can predict exactly which production you're going to end up using. So why can you do that? Why can you predict exactly which production to use? Yeah, they're completely different tokens. So L paren and number are tokens. So you know that they're going to be part of the input string, as opposed to like, program has a non-terminal as its first symbol. So in order to, you'd have to do something a little bit more clever in order to know, if program had multiple productions and all those productions just had non-terminals, you'd have to do something a little more clever. But in the case of factor, because the first symbols of each token are just, or first symbol of each production are just tokens, you can just look ahead one token and say, oh, aha, I have an L paren. It must be this production, or the input is wrong. If I have a number, I know it must be just number. Questions on this with me so far? So this is the essence of this slide. You can just make this, you can just look ahead one character or one token and check whether it's going to be an L paren or number, and use that to decide whether to use the L paren expression R paren production. So I just, in keeping with having tokens be functions, I just put the entire body as function calls, or just read a number. Make sense? So where can this go wrong? What about for this production where expression can be expanded to expression plus term? So if we could somehow distinguish between expression and term, let's assume we can just distinguish between them. We know expressions start with numbers. We know, maybe there's a way to do this. Let's say we have some if statement that distinguishes between them. Here's how we would implement the recursive descent parser for this expression production. We would, whenever we see an expression, we first call the expression function because that's the first symbol in our production. Then we call the plus token. Then we call term. So what happens here? Does this look okay? Will this work? Will you go off and write this? I'm hearing some dissatisfaction. Yeah.
What happens if we have, say, 2 plus 2 plus 2?
Well, if you have 2 plus 2 plus 2,
So it's like we have when we go into it, I'm guessing that what would normally happen, like if we had just 2 plus 2, it would be expression would get called to the 2, and then plus would get called with the plus, and then 2 would get called, term would get called with the 2. But if we have 2 plus 2 plus 2, wouldn't it be possible that term would take the 2 plus 2? Or the second set of 2 plus 2?
Well, so I think what you're starting to get at is that expression and term, they're kind of hard. You can't really distinguish between them very easily. So if you always call expression first, then you're going to end up with this infinite recursion. You're going to end up with an infinite recursion. So since we can't really tell between these two, you'll end up always calling expression as your first thing when you enter an expression, and you end up with this infinite recursion. And so this is actually a core problem with doing recursive descent, is that when you have a grammar that has left recursion, you can't write a recursive descent parser for it, or at least not for that grammar. Oh, so it means the leftmost symbol refers to its own non-terminal, as opposed to right recursion, where the rightmost symbol refers to itself. So it turns out that this kind of left recursion is not really possible. If for a grammar that has left recursion, you can't write this recursive descent parser because you're just going to end up with an infinite loop, because you're just infinitely recursing. You'll end up with a Stack Overflow, and then you go on Stack Overflow and ask why. So what do we do? What can we do about this? Do we have to give up on top-down parsing? What's that?
Some base case.
Some base case? Yeah, maybe you could kind of work out some way to do this, some way to get around it. Did you have an idea? Oh, okay. Yeah. Right recursive. So if we had a right recursive grammar, that would be like, okay, right? Because maybe that would work. But how can we get a right recursive grammar from this left recursive grammar? Is it even possible to do that? So this would only be if you read ahead in the Dragon book, you'd know this. I'm not expecting you to actually know this, But so your classmate is exactly right. If we could rewrite this grammar to be a rightmost, recursive grammar, then we might be able to do away with this problem. And there's actually a rigorous way to do this that is listed in the Dragon book. But I'll just walk you through it here before we show the formal way of doing this. So okay. So there's basically a pattern you can apply, and I don't have a proof for why that this is actually equivalent grammars. Big discrete, maybe they'll talk about it. So if I've got my left recursive grammar here, and I'll leave it to you to fill in division and modulo. So if I've got my left recursive grammar, this can be a number or parentheses. I can rewrite this using a special pattern. And now I have to actually remember what this pattern was. So let me. So the way it works is we add a new non-terminal that takes all of the stuff that was on the right-hand side of the recursive step. So we take everything that was to the right of E, and we make a new production out of that. So that's going to be the beginning of our new production. To keep the recursion, so just like there's going to be a recursion here, but we have kind of a problem here because we're not like reading the beginning of a valid or arithmetic expression. So the original E gets whatever production did not have the recursion. We take the production that didn't have any recursion, and we keep that and try to recognize our new right recursive production after the non-recursive production. So we take T, which was not recursive, we leave that inside of our original expression production and call our new non-terminal E prime. And we take the right side of our original production and make that the beginning of our right recursive production. And then add right recursion to call our new E prime production. So the intuition behind it, it's sort of hard to make this intuitive. You kind of just have to work through examples and convince yourself that it is actually works. It actually works. So one way is, okay, I'm sorry, I forgot one very important thing. So, or empty string. So to try to give some intuition about why this works is if we happen to parse something where T was the first production, then we would still be able to parse T. And when we went to parse E prime, we can just recognize it as the empty string. So that gives you kind of the base case. So this is like a kind of a formal way to rewrite it, the recursion. But if we wanted to match T plus T or E plus T, then we'd still match T. But then when we go to match E prime, that's where we get the rest of the string. Is that right? So does that any issue? Yeah.
So E prime is your recursive call?
E prime is recursive because of this, but it's right recursive now. So when we write our recursive descent parser, we're not going to get this infinite recursion as soon as we enter that. We still have recursion, so we need a way to terminate that recursion, but we'll be able to do that using predictive parsing. Okay, so what about term? How can we rewrite term? So we know we're going to have some new T prime. How can we rewrite T prime? Any takers? Yeah.
Well, for just T, it would be F. It would be F T prime, right?
F T prime, yeah, just like before. And what about T prime?
T prime would be times F.
T1 would be times F, and then the recursive T prime call,
Or F.
and then or empty string. Yeah, good. So what about F? What would F look like?
How do I just do parentheses? Or we can,
Any takers for F? Yeah,
I don't think that's actually an issue because
Yeah.
it doesn't go to F.
that's right. It's not an issue. It's not recursive. So we don't have this problem with left recursion. So it just stays the same.
Would that be considered like a base case?
yeah, that's a,
Yeah, if you tie this to recursion, the stuff that just has tokens in it is like your base case, or the stuff that doesn't have a self-reference to the non-terminal is kind of like a base case. Yeah.
So the premise of these that has non-terminals, multiple non-terminals, will have a problem with what occurred.
The grammar with multiple, even if there's a single non-terminal,
Oh, really?
you can have, if you have a grammar with a single non-terminal. It's just the recursion comes from, if you think of these non-terminals as functions, and you think of the left-hand side as a function body with a sequence of statements, if you have, the expression function, first thing it does is call the expression function, then you're going to end up with a Stack Overflow. You're going to end up with an infinite recursion. So there is a pattern that they show in the Dragon book for doing this, and I hopefully did it right, because this is always a little tricky. But the pattern is, if you have a production, and it looks very much like recursion with a base case, you've got the recursive steps here, where you have some left recursive call followed by some suffix. And you may have many versions of this, like we have E plus T or E minus T. And then you have your kind of base cases. So the term was like our base case. The way that gets rewritten is just like I said, we take the base case and put our new A prime step after it. And A prime is turned into a right recursive production by taking the suffix, the original suffix from the left recursive part, and adding the right recursive A prime after it. Otherwise, empty string. So it's just a pattern you can apply. I don't know if I'm sure somebody has done a proof for this. I don't know if the Dragon book actually shows it. But it's supposed to work. I'm just sort of trusting the authority of the Dragon book. But you can sit down and try to convince yourself of it or prove it yourself. Okay, so questions on this so far? So this is your homework for today, I think. Just rewrite the grammar with both no more ambiguity and with left recursion eliminated. Yeah.
It's like kind of like a implementation.
Yeah.
We keep everything in its own function, but then we call functions.
Yeah. So when you implement this actually takes me to the next part. Now when we got this right recursive grammar, so now expression prime, the function, just like any recursive descent parser, you just call in order the functions that recognize each symbol of the production in order. So expression can expand to term followed by expression prime. So we can just turn that into a function that called expression that just calls the term function and calls the expression time function. And expression prime can be turned into a function that just calls plus token followed by term followed by expression prime. Now that's a little harder to reason about when you have this epsilon, but epsilon is basically you call the function and it does nothing, and nothing happens. And our predictive parsing will help with that, because once we do this conversion, you'll be able to just look at the next character and know which production that you need to recognize. So if you see plus, for this particular grammar, if you see plus, that means it could not have been epsilon. And I'll go over a little more later how you do this more mechanically, how you generate a predictive parser. But I think for this version of the grammar, all of the prediction is just a token at the beginning of the production. So I think it should be straightforward. I always hate saying that because I know this stuff is kind of tricky. But it should be fairly straightforward when you rewrite this to see that every production you need to recognize, or most of the productions need to recognize, and when you need to make a different distinction between different productions, there's a token right at the beginning. So you can always just say, is my next token or is my next character the first character of one of those tokens, and use that to predict which production you need to start recognizing. Questions on this? Questions on this? Yeah.
So in that else statement down there, would you just include like a return statement or something?
No, you don't have to return anything. Well, okay, so that this when we get to code generation, then we're going to start like returning values from these expressions, but you don't have to return anything, I don't think. Yeah, you can just do nothing. You should be able to just do nothing for that. Okay. Okay, questions so far? Questions so far? Still don't know how to what?
Yeah.
The actual
implementation.
I've got my tree written down, but I don't know what the functions would be.
Okay, so implementing code for this. So I would strongly recommend when doing all these projects, instead of trying to like generate code while you're writing the parser, try just writing the parser first. Just write the recognition code, like the code that will implement the whole grammar and tell you, is this a correct string in your language or is it not a correct string? Like write that first, and then add the code generation next after that.
Oh, yeah, sure.
So I recommend doing that, making sure you get the parsing correct first, and then write the code generation.
Yeah.
Yeah. That's,
So maybe, let's see. So we'll talk about this. I think we'll talk about this in a couple weeks. I don't exactly know when. But the question is, if we're going to do predictive parsing, how do we know which production to pick? Because there's these non-deterministic choices. And so if you look in the Dragon book and look at the formal algorithms for this, there are two sets that you can compute in order to tell you which production you have to pick next. Mm-hmm. The first one is called the first set. And for any given non-terminal, it's just the set of all tokens or symbols in your language that will appear first when you're processing that non-terminal. And the follow set, and that can include epsilon. Epsilon can be the first thing you see. And the follow set is the set of all tokens that appear after a non-terminal anywhere in the grammar. The reason you need that is if you want to compute the first set for certain non-terminals, the first non-terminal of that production may be epsilon. It may be empty. So you need to know the follow set. So for instance, term can be empty. Term can be, expression. Maybe there's not an example here. Sorry, never mind. I don't have an example prepared. But if say term could be epsilon, which I know is not the case here. If term could be epsilon, then in order to find the first token of expression, the first token of expression is actually the first token of expression prime, because term could be empty. But anyway, we'll go over those algorithms later in the course. So once you rewrite this grammar, hopefully you can see that most of the productions just start with a single token. So it should be straightforward, but certainly ask questions or come to office hours if it's not, or ask on Piazza if it's not straightforward how to do the predictive parsing part. Okay, so that's all I have for this, but I think there are questions about actually implementing this. So well, so when you so for what you pass in and what you return, when you're just trying to recognize it, when you're just trying to check the input to make sure it's valid and do the parsing, you actually don't really need to pass anything back and forth. You can just start with the recognition. Eventually, you can use the return values to help you do code generation, but we can go ahead.
So our compiler doesn't actually do any math. Like we have to generate all the LLVM needs to do it all.
Yes. So the compiler is not. So an interpreter if you want it, yeah, the compiler's not an interpreter. The interpreter takes the language and actually executes your program. The compiler just translates it to another program, usually a lower level code like assembly or LLVMIR. So yeah, you don't have to do any computation about of the program you're given. You just have to translate it to LLVMIR. Yeah.
So for the recognition, should we include recursion in that?
Oh yeah. It should be. It should definitely. I mean, it has to be recursive, or you have to use a stack in order to be able to recognize these recognize an input in a context-free grammar. So it's not possible to do it with like a state machine, for instance, finite state machine, with if the language is infinite. So let's see. Here's the choose your own adventure. What do you want to see next? Should we do maybe a derivation of this grammar, like show what the parse tree will look like? Should I talk about the target language? Yes, of that? Okay. Okay, let's do that. Oh, the other options are we could talk about the target language. We could just like go home.
Ooh, no.
Oh, we got a no, and I didn't hear any other no's. So,
Tempting, but.
all right. So let's try doing a parse tree for this right recursive version of our grammar. So I'm just going to rewrite it here, so I don't forget. And please let me know if I make a mistake. Okay, there's our grammar. So let's pick. Let's just do something simple without parentheses. Let's do 2 plus 3 times 7 again, since that was what we looked at before, which sort of led us to this ambiguity. Okay, so let's assume the starting symbol is E. What production do we apply for E? Well, there's only one production, so let's apply that. T E prime. Now this is where it gets a little bit more tricky. So if we see T must be F or T prime, F followed by T prime. And if we see F, we must see a number. That's our first input. So to put this, like, think about parsing a little bit more here. If we start, we start before the first character in the input. We start here at the first character for input, and 2 is our look ahead. So we look ahead at 2, and we use that to make decisions about what productions to use. In this case, the E and T, there is no decision. There's only one production possible. But for F, we have a decision between number and parenthesis. So our first input is a 2, so it must have been the number, must be the number production. So what about T prime? So for T prime, the next character is a plus. It's a plus. So for T prime, we have 2 choices. We have either star or empty character. It means it must be empty, right? Because the next input is a plus. So we can match the empty string. So T can match empty string. And I hope this works out in the end. So T must have matched empty string, because our look ahead token is a plus, and there's no choice. It's not a star, so we have to pick the epsilon. So when you're implementing this, your T prime function will say, is it a star? If it's a star, then if my look ahead is a star, then I know I'm reading star F T prime. Otherwise, it's just empty, and I do nothing. I don't consume any input. Yeah.
So there's plus and I guess multiplying would count as your conditionals for determining whether to.
Well, any token in your input will be the conditionals. So so for predictive parsing,
I mean, just for this.
in this case, yeah. But you can generalize it more by just looking at whatever the first token of your production is. That's going to be your if conditional, because that's going to decide between these two alternatives. Just like when you hand wrote the lexer, whenever you encountered an alternative expression or alternative operator, you just check to see the next token and see which alternative you take. So it's the same thing here, more or less. So sometimes the first token or the first symbol will be a non-terminal, and then you have to do something a little more clever. You have to figure out, recursively find the first symbol of that. But I think for this grammar, I think it should be hopefully it's evident enough. We'll see when you implement it, but just figure out the first terminal that it could be, keeping in mind that it could also be the empty string, like in this case. So that so it's kind of like the else condition for epsilon. Okay, other questions on this so far? Okay, so let's continue. So now we have to process E prime. So again, we've got two, I'm afraid this, yeah, sorry, no, okay. I was confusing myself. Okay, we've got E prime. And so with E prime, we've got two possible productions, plus T E prime, or just epsilon. And our look ahead token is plus. So which production do we pick? The plus T E prime. And so this works just like the T prime function. You check your look ahead and say, is it a plus? If it's a plus, then I know I'm processing plus T E prime. So here's my parse tree, plus T E prime. All right, so now I'm on T again. So T only has a single production. So it must expand to F T prime. And now I'm back at F. Oh, I'm sorry, I forgot to advance my look ahead. So after I consume plus, so the look ahead, yeah. So whenever you actually see a token in your production, that tells you you got to consume the input token and move on to the next one. Sorry, I neglected to do that. But when we were on E prime here, and when plus matched the first token, I wrote it as calling the plus token recognizing function. But what that ultimately does is it consumes the input. You're gonna if you wrote your lexer in the way I suggested, that function is going to call fgetC, and it's going to advance the pointer in the file past plus. And then 3 will be sans white space. I'm assuming you're handling white space. 3 will be the next token in the input beyond that. So 3 is our look ahead. We haven't yet consumed it yet. And F is our current production that we're trying to derive. So for F, we see a number. So what's the production we use? The number production. Now we have T prime. So in this case, our look ahead, after we consume 3 because we saw number. So now our look ahead is on the star symbol, and we're trying to reduce trying to substitute T prime. So T prime, there are two options, star F T prime or epsilon. So which production do we choose? Star F T prime, because that's our look ahead token. So we process star, and that moves our look ahead token. And then we have to process F and T prime. Okay, so now we've got F, and our look ahead is the number 7. So we reduce F, the production that takes F to a number. Now we've still got T prime. Now we're at, so in the Dragon book, they're going to use money sign as a sentinel for the end of your input. So we can, it's a kind of a formal convenience. So this is like EOF. If you're on EOF, you can use EOF as the sentinel. So that's our look ahead. Our look ahead is EOF or this sentinel. So if we see T prime and we've got EOF, what production must we match? The epsilon production. So T prime is going to be epsilon, and now we're on E prime. What production must we match? Epsilon. Okay, I thank God that worked. I was worried at first.
Yeah.
What? Okay. Okay, actually, I think that was good to go through that because that sort of illustrates how your predictive parser is going to work. So you can think of each one of these steps, each one of these tree nodes as a function call, and the child nodes as like recursive function calls. So if we recursively call T, this is going to end up being a post-order traversal where T, the E is going to be called first, T is going to be called second, and then F is going to be called third, and the number token is going to be called, it's going to be consume input. T prime is still going to be called, even though it's matching epsilon, it's going to be called, but because the look ahead token doesn't match any of the productions for T prime, it's just going to do nothing. It's not going to call any other functions. It's not going to consume any input. It's just going to do nothing. And then we're going to, pop back up, start processing E prime, because once we return from T prime, we're going to return to T. Once we return from T, we're going to return to E. And then the next statement inside of E is going to be calling E prime. Does everybody see that? Do you want me to write some pseudocode? Yeah.
Just to make sure, the pound sign in terms of our project would be a semicolon, right?
The pound sign? Oh, I'm sorry. This is a money
Right,
sign.
sorry.
This is a money sign.
It would be a semicolon.
No. So semicolon is part of your grammar. That's a symbol in your input. This is like EOF. This you can probably just use EOF or make a special So if I gave you 2 ways to write the lexer. Maybe that complicated things. But if you wrote it where you're tokenizing the input first, then you could just create a special token, a special kind of phony token called like end or whatever. If you're just doing fgetC, then EOF is like your end token. So if we kind of look at the like pseudocode for, let's look at the pseudocode for like T prime. So if I've got this function T prime, so this is my function T prime, and its first order of business is to decide which production it's going to use. So it can check my look ahead token. Oh, that is laggy. If the look ahead token is star or times, however you wrote your lexer, then we know it's going to be the first production. So this is my like times token function, which is going to consume the input and move the look ahead. Yeah, just like fgetC or go to the next token. It's yeah. That's like the kind of technical compiler-y word for they say consume input. And then it's just going to call the f function and recursively call its own T prime function. If it doesn't match, if none of the look aheads match any of its productions, then it's just going to do nothing. Yeah, it just returns. So one extra kind of wrinkle. Let me just make questions on this. Does this make sense? Yeah. The times token function. So that's kind of calling into your lexer. So here at this point, you could. There's several ways to implement this because context-free languages can also recognize regular languages because it's a superset. So you can actually take the lexical specification and just encode that as in part of your grammar. I didn't really go over doing that, but you could totally just do that. So this function, I'm just assuming it's like calling fgetC and reading as many characters as it needs to get the token. And then getting rid of white space and setting up the look ahead so that it's looking at the next character or token. So I think you could do this by just using fgetC because I think you can distinguish the beginning. You could look at the beginning of the token itself. Like in my slides, I had to check if it's a number, I check if it's minus sign or digit to see if it's like a number. Yeah.
I know you don't want us to worry about printing out and all of that, but would that be a part of some of these at this point?
Oh yeah. So so once you have this kind of skeleton of the parser that can consume the input, read through all the input and not fail.
Terms, and then we need to get the temporary variable.
Right. Yeah.
Stuff
So
like that.
yeah. Then for code generation, so this change of the grammar makes code generation a little bit more annoying because your term or your expression may be spread across two different functions.
Right.
So that's going to make things a little bit more annoying, but it's still doable. But ultimately, what you want to have happen is
I feel like the term function is really zero. But maybe, I don't know.
I can't.
I'm not sure.
Yeah, I
Maybe
can't
they all do
determine
it.
that
Never mind.
necessarily.
so what ultimately you want to have happen is for each leaf. Well, okay. So ignoring the tree for a second. So just looking at an expression. So what you hope will happen if we look at the unmodified tree, what you want to have happen is you do a post-order traversal of this, and this node is going to be processed first. So what you hope to have happen is that IR is going to be output first,
Yes. Yeah.
and it's going to record its intermediate value and somehow communicate that intermediate value to its parent.
Right.
So just like the left-hand side communicates the number 2 to its parent, the right-hand side communicates the variable that it's using. So that way, yeah. So there are lots of ways to do this, but you can exploit the recursive nature of this to do returns. So then when I compute, so this is the first statement. This is the second statement. Right. Exactly. So 2 plus T1. That's what ultimately we want to have happen.
So you could start like operator 1 to follow the first tree that it descends, and operator 2 to descend.
I'm not sure.
Well, you have equal operators because we could have like.
Well, if you were starting from the very beginning.
Yeah.
So what makes it a little trickier is that E prime is only part of your expression. So you're going to have to communicate that back to your root.
If you could print out, a pen to print.
You might be able to play with printing. You might be able to play with printing to do this. But think about this. We'll talk about code generation next time. But I would, if you want to get started on this, you can really just start writing the recursive descent parser and getting it to recognize the input. And I recommend doing that first anyway.
That I think is right. I didn't know how to. What do I do with the information that I have?
Yeah.
We're just dumping it at that point. It's just going even nowhere. So that makes sense. Okay.
Yeah, it's just a recognizer at this point. It's not really a compiler. It's just recognizing the input. All right. Thanks, guys. Oh, I went over. Sorry about that.